Bismillahirrahmanirrahim. Today we'll again talk about the Kleene theorem and we will complete the third part of the Kleene theorem. The third part of the Kleene theorem is that if a language is accepted by a regular expression, then it can be accepted or it can be converted into the finite automata. How we can prove that? We can use some constructive algorithm starting from the recursive definition of a regular expression. First of all, the recursive definition of a regular expression is for every letter in sigma, the letter written in the bold is the regular expression. And we have empty is also a regular expression. So if R1 and R2 are the regular expression, so we can have the R1 plus R2, which is basically known as the union or the addition. R3 is basically the sum of R1 and R2, no matter whatever is the regular expression. If R1 and R2 are the regular expression, so we can also perform R1 dot R2, or you might call it as the concatenation. If R1 is the regular expression, so we can also take the star closure. So let's assume we have this as a regular expression 1. So here what we did, we take a star closure. Nothing else is basically a regular expression as per the Kleene theorem. Let's solve the part 3. First of all, in here, the first one, this is basically the first part, which says that there is a finite automata that accept any particular letter of the alphabet. So there is a finite automata that also exists only the word which is the lambda or the null. So here you can see this is my starting a node or a state, and this one is final. If x is in sigma as an input, then this diagram will represent actually what represent the it will only accept x. It represents a finite automata that only represent x. Here this finite automata only accept empty lambda. Why? Because here this is the initial as well as the final. Here it is like a dead configuration. Let's see the rule 2. If there is a finite automata called FA1 represented by regular expression 1, another finite automata known as FA2 represented by regular expression R2, then what we did, we can take R1 plus R2, we can call it as union. How we can solve it? Let's consider one of the example. Let's assume here there is an example which of a finite automata which consists of two A's, and here there is a finite automata in which both both have an even of number of total A's and B's. So this is basically even example. Now, in order to perform the union, first of all, what we did, we will take the initial state of one finite automata, and we all can also take the another, this is finite automata 1, FA1, this is FA2. So I need to take the initial states of this, and I assume that Z1 is equal to X1 or Y1. As Y1 is also a final, so we make it as initial as well as the final. Now let's start creating the transition table. So we will first start with Z1. So for Z1, what I need to do is that we know that Z1 is equal to X1 or Y1. So in this diagram, if you can see for X1, the path of A is X2. For X1 to A is X2. Y1 to A is Y3. So here we have X2 or Y3. Now this is basically what? This is basically my dictionary where I have defined the Z. So you can see I only have Z1. I don't have any combination of X2, Y3. So that's why it is written Z2 is equal to X2 or Y3. Now I need to see the path for the B. Now in order for the path for the B is for X1, if it is B, it will be X1. For Y1, if it is B, it will be Y2. So it will be X1 or Y2. Inside the dictionary, we don't have that thing. So that's why we define Z3 is equal to X1 or Y. Here it is Y3. Sorry, Y2. Here it is x1 or y, z3 is equal to x1 or y2. Z3 is equal to x1 or y2, and z2 is equal to x2 or y3, because for y1, if we have a path of b, it will be y2. So here we have written z1 is equal, and for a it is z2, for b it is z3. We will continue now for z2, which is equal to what? Z2 was basically equal to x2 or y3. So here from x2 to a is x3. From the y3 to a is basically y1. So we don't have any combination here. So that's why Z4 is equal to X3 or Y1. Now let's see for the path B, as Z2 is equal to X2. So X2 for the B is X1, and Y3 for the B is basically Y4. So again, we don't have any combination here. So we define it as Z5 is equal to X1 or Y4. And you have here Z4, here you have Z5. Okay, now let's see here. Let's solve it for Z3. Okay, Z3 is equal to X1 or Y2. So X3 to basically A is X2. It is X2. And Y2 to A is Y4. Okay, so Z6, we don't have a combination here. If you can see the combination here, we don't have X2, Y4. So we have added here X2, Y4, which is equal to Z6, and we have added Z6 here. Now, for X1 to Y to B is X1, and Y1, Y2 to B is basically what? Basically equal to Y1. So which is equal to X1, Y1 is equal to what? It is equal to Z1. Similarly, we solve it for Z4 as well, the same steps. For Z4, when we do that for Z4, we came up with a combination for A is X3, Y3. So X3, Y3, we don't have any combination. Here we added a new case, which is, state, which is Z7, which is equal to X3, Y3. For B, we came up with X3, Y2. We didn't find anything here related with X3, Y2. So we have added a new state, which is basically equal to Z8. So here, Z4 to B is basically Z8. Similarly, we performed the same step for Z5. And when we did for Z5, we came up with Z9 and Z10. Similarly, same steps. Yani Z5 is equal to X1, so X1 to A, and Y4, Y4 to A. Similarly, for X1 to B and Y4 to B. We did it for Z6 as well. When we did for Z6, which is equal to X2, X2 to A, and Y4 to A. Then X2 to B, and then Y4 to B. So we came up here with we have some new entries. Okay. So what we did, we already have here Z8 was there. Z8 is equal to X3, Y2. So we didn't add anything in the dictionary. Same is the case Z10 was here. So we don't need gray in color indicate here, indicate that, those states already exist. Similarly for Z7, what we did for path A, we have Z4. However, for path B, we define a new state, which is basically Z11. So here is Z11. Same is the case for Z8. Okay, we see the path for A and we see the path for B. So here for the path A, it is equal to Z11, and for B, it is equal to Z4. We did the same thing for Z9. Z9 to A is Z11, and B is basically Z1. Z10 define the path for A and define the path for B. So for Z10, for A, which is equal to X2Y1, in here, we don't have that combination. That's why we added a new state. So for A is Z12. However, for B is, which is X1, Y4, which is equal to Z5. So here we wrote Z5. Now Z11 is basically equal to X3Y4. So we have seen the path for A and we have seen the path for the B. Okay, we got yani X3Y2 which is equal to Z8 and X3Y3 which is equal to Z7. So here we have Z8, here we have Z7. And then we have the state, which is Z12, which is equal to X2, Y1. So X2 to A, Y1 to A, X2 to B, and then Y1 to B. So we came up for A, it is X3, Y3, which is equal to Z7. And then here for B, it is X1, Y2, which is equal to Z3. Now we left with no more states. So khalas, here we will stop. Now, in order to decide which states are basically the final states, out of all these, which is defined in this dictionary, we will see all the states that consist of either, this X3, okay, or Y1, or maybe both, they are the final states. So you can see in here what we have, if we will see these ones, okay, in here, what we did, we have Y1 as a final state, okay, so that's why it is final. In this one, we have X3 and Y1, both they are final. That's why we make it as final. Now, in here also, you can see we have, X3 as a final. Here you have X3 as a final, so we make it as final. And here you have basically, X3 as final. Here you have Y1 as final. So those are the final states, and it will always have a single or one initial state. So this is basically the definition of all Z's, and here is the transition diagram. From this you can easily generate the finite automata. Let's consider another example. In this example, having two A's somewhere, and there is another finite automata which end over B. So here, first of all, we will create what? We will create the transition table for these two finite automatas. Now, after that, what we will do, we will start with the first one, okay? X1 as an initial state and Y1, Z1 is equal to X1, comma, Y1, okay? Here, as those are not the final state, so it is now only as the initial state. Now, let's trace the path. For X1 to A is basically X2. For Y1 to A is basically Y1. X2, Y1 was not defined here. So that's why what we did, we add a new entry in the dictionary and we wrote here as Z2. Now, X1 to B is X1 and Y1 to B is Y2. X1, Y2 was also not here. So what we did, we assume Z3 is equal to X1 or Y2. And here we have the Z3. Now, let's decide the final states at the end. Now, let's start with the other one, which is equal to Z2. So, Z2 to A is X2 to A is X3. Y1, because Z2 is equal to X2, Y1. So, X2 to A is X3. Y1 to A is Y1. So, X3, Y1 will be equal to Z4. And here we will write Z4. Now, X2 to B is X1 and Y1 to B is Y2, which is basically equal to what? Which is equal to X2, X1 or Y2 is already defined here. So we'll write it as here Z3. Now Z3 is equal to X1 or Y2. So X1 to A is X2, Y2 to A is Y1. So we have here X2, Y1, which is equal to Z2. So here gray color indicate it's the entry is already there in the dictionary. So that's why here we will write Z2. Now let's see B. X1 to B is basically X1 and Y2 to B is basically Y2. So it is basically what? It is equal to X1, Y2. X1, Y2 is equal to Z3. So that's why here we wrote Z3. Now we will write Z, we'll solve it for Z4. Z4 is equal to X3, Y1. So X3 to A is X3. Y1 to A is Y1. So it is X3, x3 or y1. If we will this list one by one, so it is equal to z4. So we wrote here z4. Now here for x3 to be is x3 and y1 to be is y2. So it is x3, y2. If I will see it is not equal to any one of them, so that's why we define a new state which is equal to z5 and we wrote z5 here. Let's solve it for z4. Z4 is equal to x3, y2. x3 to a is x3. Y2 to a is y1. So now I will see, okay, do I have x3, y1? Yes, which is equal to z4. So I wrote here z4. Here we wrote what? We wrote z4. Now x3 to b is x3 and y2 to b is also y2. x3, y2. What I will do, I will go one by one until and unless what I found the, a new, a state that is already there. Basically, it was not there. What we did, we defined a new state which is equal to z5. So z5 is equal to what? Z5 is equal to x3 or y2. Then ultimately at the end, what we did, we need to solve it for z5. And we know that z5 is equal to z5 is equal to x3 y2. So here x3 to a is basically what? Is basically x3. Y2 to a is basically equal to y1. So do I have x3 y1? Yes, which is equal to z4. So that's why here it is written z4. Now let's see for b. Now x3 to b is x3. Y1 to b is y2 to b is basically equal to y2. So we have x3 y2. If we will see, do we have x3 y2? Yes, which is equal to z5. So here what we did, we wrote z5. So here is basically the transition table. Now, in this case, in order to decide which states are the final states, so we will see all the states in which we have either, x3 or y2, or maybe both. Even if one of them is there or even both is there. So in this case, you can see no final state. In this case, yes, we have a final, which is y2. So that's why we make it as final. Here you can see we have x3 as final. That's why we make z4 as final. Here, if we will see in this particular case, what we did, we have y2 as well as x3, both are final. So we also make this as final. So for this particular question, here is the transition table and here is basically the diagram. Here is the exercise. You have this finite automata of all ending over a. This is another finite automata having odd length. When you apply a union, what you will get, you will get this one. So you can solve this example by yourself. That's all about the union. If how we can, if we have two finite automatas, how we can convert those finite automata into the regular expression. For that, what we need to do is we need basically, we need to, how we can basically even combine it by doing some sort of concatenation and union. In this, lecture, we talk about union. In the next lecture, we'll talk about the concatenation and the star closure.